Welcome student, my name is Kuldeep Singh Solanki and today we are going to discuss the deflection of beam. This is a part of theory of structure. In previous lecture we have already discussed the static and kinematic indeterminacy, and in this lecture we will discuss the deflection of beams. Now we starts. And deflection of beam. What is the deflection? It is the transverse downward movement. Okay, it is the transverse downward movement and vertical distance in transverse direction between position of axis before and after loading at the section of the beam is defined as the deflection of beam. And see the figure, this is a simply supported beam, and if we are applying the load W at central, then the beam will deflect. In this case the beam will deflect from A to B, and this is a green line, so the deflected shape of the beam. And the vertical distance, suppose that it is deflected in central position from C to C dash in vertically, so this is called the deflection. It means beam axis is horizontal, or this is also called undeformed axis, and after we applying the loading, the neutral axis of the beam or beam axis will deflect in this manner. So the vertical distance is called deflection of beam. So in this case del C, it is the deflection at that C. And next is under the action of external load, any beam bends and suffer deflection at various points along the length. It means if you are applying the loading, and deflection will be vary from length to length, and the deflection is caused by bending moment acting at various sections of the beam, and deflection is also caused due to shear, but a magnitude is small compared to that due to bending, hence it is generally neglected. So the deflection is caused by due to moment, bending moment, and due to shear. So but the deflection of shear is very small or minimum, so we can neglect the deflection due to shear force, and we will consider the deflection due to moment, by the moment. Clear? Deflection due to shear force is very minimum or small compared to bending moment, bending deflection, so it will neglect, it can be neglected. So elastic curve, it is also called the deflection curve. What is the elastic curve or deflection curve? The deflected shape of beam axis or deflected shape of neutral axis is called elastic curve or deflection curve. Suppose this is, see the figure, this is the simply supported beam, and ACB, this is our beam, and also ABC is a horizontal direction, our neutral axis is horizontal, or beam axis is also horizontal. So if you are applying the load W, the beam will deflect like ADB. Okay, this is a deflected shape of the beam, and this deflected shape form a curve. This curve is called deflection curve or elastic curve. This is a deflected curve of the neutral axis. This curve is called elastic curve or deflection curve. And differential equation for elastic curve, the elastic curve have the equations. This is the EI d square y upon dx square equals to m. This equation is for deflection curve. This is the curve equation, EI d square y upon dx square equals to m. E is the modulus of elasticity, I is the moment of inertia, and m is the bending moment due to external loading. And next is slope. What is the slope? Slope is the angle between before neutral axis or beam axis and tangent of deflected shapes. Okay, if you are calculating that angle at A, and first we draw a tangent at A, and angle between the tangent and undeformed axis, and also called the neutral axis, and also called the beam, axis of beam. So the angle between tangent and axis of the beam or undeformed axis is called slope. we can calculate slope anywhere from A, B and C, anywhere of the beam. So the slope of the slope of the beam at any section is defined as the angle, an angle in radians of inclination of the tangent drawn at that section to the axis of deflected position after loading, measured with respect to undeformed axis. So this angle is measured from undeformed axis, also called beam axis, also called neutral axis, is measured from neutral axis and tangent, and at any point draw the tangent and measure the angle. This angle is called slope. Next is assumption made in the deflection. Some assumption will made in the deflection theories. So first is axis of beam is horizontal before loading, and we know that beam is horizontal member. Okay, and deflection due to shear force is negligible. Okay, because shear force deflection due to shear force is very small compared to the moment, so we can neglect the deflection due to shear force. And simple bending equation, this is m upon I, sigma upon y and E upon r, is this is a bending theory equation is applicable, and all the assumption made in simple bending theory, and all the assumption of simple bending theory is applicable. And material of beam is homogeneous, elastic, isotropic and obeys Hooke's law. It means material is homogeneous means the property of material at every point, property of material at every point is same, is called homogeneous material. Isotropic is the property at property of all direction is same at every point. Property of all direction, it means x direction, y direction and z direction at every point is same, is called isotropic material and obeys Hooke's law. And Hooke's law, what is the Hooke's law? Hooke's law, up to the proportional limit, stress is directly proportional to strain. This is called Hooke's law. All are valid. And the modulus of elasticity is same in compression as well as in tension. So modulus of elasticity, it is equal to E, and it is same, it is the material property, so it is same both in compression and tension zone. In plane section remain plane before bending and after bending. It means our strain curve is linear. Plane section remain plane before bending and after bending. It means our strain curve is linear. So it is clear all the assumption for deflection. And sign convention. Sign convention for horizontal distance x. For horizontal distance x, if you are travel from left to right, then it is positive. When measured from left to right, measured, it is positive. And for vertical distance and above the neutral axis is positive and below the neutral axis is negative. So when the measured above the axis, neutral axis, beam axis, okay, this measured above the axis is positive and below the axis is negative. And bending moment is the clockwise bending, clockwise moment is positive and anti-clockwise moment is negative. So this is the sign convention for deflections. And next is simply some important terms. First is simply supported beam, and see that this is a simply supported beam ACB, and a point load W is acting at the central point C, okay. And in this case, A is simply supported, A is simple supported and B is roller support. A is pin support, also called pin support, and B is roller support. And we know at A is deflection is 0 because supports are available at A and B. Supports are available at A and B, so the deflection is 0. At A deflection is 0 and at B deflection is 0, but at A slope is not equal to 0 because at A slope is maximum. Slope at A is maximum, and also slope B is maximum because this is the symmetry of beams. So slope at A and slope at B is equal, and this is the maximum slope. And deflection at central portion is maximum because at A deflection is 0, at B deflection is 0, and deflection will increase from A to C, and maximum deflection is at central point or also below the point loading. This is a maximum deflection, and at C, central portion at C, C theta equal to 0, 0, it means the slope is 0 at C, because at C our deflected shape, if we are draw the tangent at C, then our tangent is horizontal, and also we are measure the angle from horizontal axis or neutral axis. Our neutral axis is also horizontal, so the angle at angle at C equal to 0. Now deflection y, A and B are 0. Deflection y at A and B are 0 because it is the supports are available, and maximum deflection at middle span, it means maximum deflection at C below the point load, and slope is maximum at A and B, and slope is 0 at middle span. Slope is 0 at C because tangent and neutral axis in same or parallel, so angle is 0. So next is cantilever beam. Cantilever beam, this is a cantilever beam fixed at A and free at B, and in this case at A supports are available, so deflection is 0 at A, and supports are available, so theta is also available because at fixed end resisting moments are available, so rotation is 0 at A, and also deflection is 0 at A, and at B deflection is theta B. This is the maximum deflection. Deflection will increase from A to B, and maximum slope also at B. So deflection y and slope theta both are 0 at fixed end, and slope and deflection are maximum at free end. In case of cantilever beam, slope and deflection both are 0 at fixed end, and slope and deflection is maximum at free end in case of cantilever beam. But in case of simply supported beam, support A and B on the supports, deflection is equals to 0 and maximum deflection at the center, and for slope, maximum slope for simply supported case, maximum slope at A and B, and minimum slope or slope 0 at central point, it means C. Okay, now it is clear. Next is some method of finding the slope and deflection. This is some methods: double integration method, Macaulay method, area movement method, and conjugate beam method, and unit load method. This is all the methods to find out the slope and deflection at different positions on the simply supported beam and cantilever beam, or different types of beam and different type of loading. So for diploma case, only 3 methods are in syllabus: double integration, Macaulay method, and area movement method. So in next class or next lecture, we will discuss one by one double integration, Macaulay, and area movement. That's all for today. Thank you.